Yeah, so our next speaker is Pasham. We're talking about recurring ultrafast outflows for repeating extragalactic X-ray transits and potential unification. So,
Thanks. So yeah, good afternoon, everyone, and thanks for being here. Special thanks to the organizers for organizing this super exciting conference. I was very excited when I first got the email. I was like, "Well, this is like perfect timing to do this." You know, get all the theorists and the observers fight with each other in the room. You know, yeah, looking forward to many discussions this week. So I'm going to maybe change the tone a little bit from what Ricardo had in his. So in my presentation, I'm going to talk about repeating extragalactic X-ray transients, and then a potential model as well. I know today is not theory, but I'll mention a little bit of that to excite people and also like make people angry. So yeah, what do I mean by repeating extragalactic X-ray transients? We've heard about QPOs already. But I'll argue that we have two other types of repeating extragalactic transients. These are the traditional QPOs, quasi-periodic oscillations, and also these quasi-periodic outflows, which is a new phenomenon that myself and other people have identified recently. These are papers currently under review. So just to give you an example of each, what is a QPO or a quasi-periodic oscillation? So these are systems that have existed in literature for a while. But the ones that are relevant here are the ones that are highly stable. So this is one such example of an AGN, which is soft, very soft AGN. And then here is an X-ray light curve on the y-axis. You have the count rate, and x-axis you have time. You see this beautiful, not actually working. All right, you see this beautiful smooth X-ray variation separated by about an hour. Yeah, so there are other AGN QPOs that are not relevant because those are not stable. So like I said, the things that are relevant are the ones that are highly stable. Another one was a TDE, assassin 14 Li, where we identified a 130-second highly stable QPO as well. So you already heard about QPEs, the second transient, so kind of type of transients. The third one that I'm going to spend a little bit of time on are these quasi-periodic outflows. So this is an example where on the y-axis, I'm actually plotting a quantity that tracks the strength of a specific outflow in the X-ray spectrum as a function of time. So each data point here is actually an X-ray spectrum. I'll get into details, but here what you're seeing is the outflow strength appears to be changing as a function of time. So the outline for today's talk is, first, I'm going to focus on explaining what this new phenomenon of quasi-periodic outflows, as I call it, QPOs, which are not QPOs, QPOs. And then this is the second aspect I'm going to talk about today are these outflows that may be present in all these three different flavors of repeating transients. And then I'll briefly also mention the directionality of time lags between soft and hard in the QPEs. Systems. And then the potential unification model, and then what I think is the role of TDEs in producing these repeating transients. All right, let's get into the first one, QPE outs. This began with this particular transient that was identified back in 2020. So initially it was identified in the optical as an optical transient. So you see this blue Gaia, huge outburst. And then we triggered an X-ray monitoring program with XMM, SWIFT, and also mainly NICER. So here are the archival Zeta data points. You see nothing, pretty much upper limit. And then you see 1,000 times brightening in X-rays, and then a couple of magnitudes in the optical. So what's really interesting is if you zoom in to the X-ray light curve, you see this peak. This pretty much looks stochastic. You try to take a priorogram. It's just noise, really. Nothing there, nothing that is apparent even by eye. But what's really interesting is if you look at the spectrum, like I said, here, you try to fit a thermal component. It's not a perfect fit. You take the ratio of the data to the best fit thermal component, you see these wiggles. And these wiggles can be modeled with an ultrafast outflow. And the basic idea is, so I just want to give you a basic idea of what is happening when I say modeling with an ultrafast outflow. The idea is you have a thermal continuum that is ionizing this slab of gas that is moving towards you. So the three parameters in this modeling technique are the distance of the gas slab from the thermal continuum, the temperature of the thermal continuum, the luminosity of the thermal continuum, and the speed at which this slab is moving towards you, the outflow. So we do this kind of, so there are codes to do this. They compute the ionization balances, and they try to fit the data. You go from being this wiggly to perfectly flat. And in this case, the implied velocity is on the order of 0.2c. So yeah, so you have this system that we identified.
Could you say a word about the inferred distance between the source and the gas that is expanding the outflow?
So it's on the order of a few tenths of Rg for this black hole. So the black hole mass in this case from optical spectra is on the order of 10 to the 7.5 plus or minus 0.5. So you take that black hole mass, it's on the order of 10 or 20 Rg.
Sure.
So yeah.
What was the physical process that leads to this changing spectrum? What's the physical process that leads to the changing spectrum when you're at the output?
Yeah, so that's the main point of the talk, so I will get into that.
So what is included in the model?
Oh, you mean the A-star? The A-star model? The one, this one?
What used to produce the plot on the bottom right? What is the physical process?
Oh, this one?
Yeah.
So what I'm saying is, this is the ratio of the data to the best thermal model.
Yeah.
It's not flat, right?
That's it.
So if your model is describing your data, it should be flat.
Yeah.
So what I'm saying is, if you include the ultrafast outflow, then it becomes flat, meaning you're doing a good job explaining.
Yeah. My question is, what is included in this outflow model? What leads to this energy? What leads to the changing spectrum?
I'm not entirely sure I actually understand. What do you mean change in spectrum?
I mean, here, basically the model, the spectrum that you modeled changed from the upper.
So yeah, so the upper one is just a sample spectrum. And then what I'm saying is, if you include the outflow, then you're able to account for all the spectral wiggles. So you go from like whatever reduced chi-square of 10 to like reduced chi-square of 1 is what I'm saying. If you include the outflow in your energy spectrum.
I'm trying to understand too. Is this like a P Cygni profile?
No, it's not a P-Cygni profile.
Okay,
Good
good.
question. It's all absorption. There's no need for emission. So P-Cygni is when you have both
Okay.
emission and
Sure,
absorption.
right.
Here, it's just absorption. This bump that you
What's
see
the bump?
here,
Yeah, the bump's
it's
throwing
just
me.
a distortion of the continuum because of the broad absorption line. So this is basically modeled with an oxygen 8 or 7. I have to check, but it's one of those lines, absorption line.
Okay. So this is pure absorption.
Yes. When you fit it, when you look at the resulting best fit, there's no need for emission. It's just all absorption.
Okay, and your absorption line has a velocity offset
That's correct.
relative to what? That's how you're characterizing the
Relative to
outflow.
the rest frame, if it's oxygen 8, then 0.585, I think is the rest frame, KV. And it comes at 0.85, so, you know,
Oh, okay, I
0.85
think
minus
that's,
1.
is that what you were asking?
Yes.
Okay,
Cool. All right, sorry.
And one last question is essentially with one line, or there are a few lines that you can use to get consistent results with this 0.3C in this case, for example?
So, well, it's a combination of many lines, but the main one is the oxygen.
Okay, thanks.
Right. So we can model the spectra with an outflow present, but for the very first time, I mean, it's difficult. It's always like pretentious to say very first time, but this case, I think we're pretty confident that for the very first time, we could actually track a supermassive black hole's outflow as a function of time. So we can actually track the strength of this outflow as a function of time, thanks to NICER. So people who don't know, I'm showing you this NICER slide because part of this trip might be funded by NICER as well. So NICER is an X-ray telescope that sits on the International Space Station. And what's really great about NICER is for bright targets, it is 1.5 times better than XMM Newton. And the key thing that NICER brings to the table is that NICER is able to monitor to pretty much any part of the sky very quickly, which XMM cannot do. So that is the reason we're able to track it for extended periods of time. And like I said, we can track the strength of this outflow as a function of time by simply taking the observed count rate. So not model dependent, model independent, observed count rate in this band and divided by that band just to normalize all the stochastic noise. And that is what is shown here. So it's the ratio of the count rate in that outflow band divided by the continuum. So high value means the outflow is actually weaker, and low value means the outflow is stronger, right? Because it's a dip. The stronger the dip, the stronger the outflow. So this is how it looks like. You can do your usual timing analysis. As expected, the peak shows up at around 8.5 days. Yeah, about 4.2 sigma. What's really interesting is you can also do more. You can actually track, you can actually get the spectra from these low points, high points, and then model it with the same thing that I described earlier with an ultrafast outflow. And we find that consistently weak outflow, strong outflow, weak outflow, strong outflow. So during the green phases, the absorbing column is on the order of 10 to the 22. During the during the strong outflow, the absorbing column is on the 10 to the 22. In the weak, it's on the order of 10 to the 21. So it's a factor of 10 less dense. So you have these cycles of strong, weak outflow. So just about when we were ready to submit this paper, Muriel, who was a graduate student at Johns Hopkins, he found this other system, which is in the bottom panel. So this is the source that he found. And what he's showing here is just the X-ray count rate as a function of time. And notice the time scales. And he's comparing that with Euroqb1 and Euroqb2. So here, this system appears to be repeating, well, quasi-periodically, once every 20 days. And we call it the crazy fifth source. So it's the same light curve in the top panel extended to much further out. In the middle, I'm showing you NICER data, which again has much larger effective area to actually can get spectra. And then what's really interesting is we actually detected transient radio emission. So these are VLA data points from Kate Short and James Miller Jones's large VLA program. Luckily, they observed this target. Not sure why, actually.
You asked us to. I think you asked us to.
Okay. So anyhow, they observed this target. And then during the quiescence, there was no radio detection. But like right at one of the X-ray bursts, we have a clear radio detection. And what's really even more interesting is that if you do phase resolved spectra in the X-rays, and you take spectra from rise, peak, and decay, which are shown here, during the rise, in all the spectra, you see sort of like a bumpy feature, which can be modeled with an ultrafast outflow. So consistently during the rise, there appears to be this feature which can be modeled with an ultrafast outflow. And then again, that is where also the radio detection was made. So if this is a QPE system, then it will be the first QPE with transient radio emission.
What are the different colors? There's a black ratio, green ratio, and a yellow ratio. I'm just trying, as you step
even
down.
these?
Yeah, what is all?
I'm sorry, yeah. So the magenta is
That's
for
at different
rise.
times.
Yeah,
Okay.
this is the rise. So all the rises are in magenta. And the cyan is for the peak. And then yellow is for the decay. So.
Okay, so
this
you're
is
saying
ratio
during
for
the rise and the peak, you're detecting what you think is some kind of outflow and not necessarily during the at
decay.
longer times.
Yeah. So, you know, it's strongest during the rise, and then it gets a bit weaker, and then pretty much consistent with just the thermal component during the decay.
Okay.
Is it possible to estimate how much mass is ejected or energetics of each outflow?
Yeah, I mean, totally, it is. It's in the paper. I have to look into it, but yeah, we did that. Yeah, I can tell you later.
Okay.
I mean, can you tell us if it's how many kilometers per second is it order of magnitude?
The M dot, you mean M dot out?
Sure, yeah. Or just the speed of the outflow. I'm just trying to get a sense.
So, yeah, the paper's right here.
I'm sorry.
Well, the earlier one was 0.3 C, but
Yeah, that was.
This
fast.
one was like 0.15 C, I think is the best fit.
So that wasn't a fluke, because they're all really fast, ultra fast.
Yeah, so. Yeah, here. That's the table. So I guess it's 0.1 C.
Thank you.
So those are the NH values.
We must, since you're on the paper.
M dot out. M dot out. Okay, M dot out is, oh, here's M dot out. So you also have the E dot out. Oh, here. I moved the cursor. So it's 10, few times 10 to the minus 3. Few times 10 to the minus 3. Solar. Yeah, which corresponds to that. And those are the numbers. Cool. So we had a system which showed the modulation just in the outflow band. And we had the system which shows it both in the continuum and also in the outflow band. So it was just natural for me to just say, why not go back into the QPE archives and just like look into it and see if QPEs have the same thing. So the thing I did was look at one of the XML observations from Euroqb1. Right here, I'm showing you the spectrum that is taken by combining the data during the decay. You fit a thermal component, the ratio looks like this. You can model it within outflow. So Johin is actually working on it quite a bit. And there are some subtleties here in the fact that the temperature is changing, so you have to stack the data because the temperature is actually evolving during the time. And I've taken everything averaged over that temperature evolving thing. There's also tests we have to do to make sure, we are seeing a real legit outflow as opposed to a combination of several disk black bodies with changing normalization and temperature. So now, go back to the QPOs that have already been published for a long time. So this is REJ 1034, the one with 1 hour quasi-periodicity. And there was actually a paper published by Dipankar Maitra and John Miller back in 2010. What they did was they basically looked at stacked X-ray data from just the peaks and the low points. And when they do that, what they find is that during the red, you fit it with your disk and thermal disk and corona, it is flat. However, during the low points, there's actually bumps and wiggles, which can be modeled with an outflow. So phase-dependent outflows was claimed in this paper as well, going back to 2010. So the natural thing was to also do the same thing for Assassin 14Li, which has a QPO of 130 seconds, which was highly stable for about 500 days, beyond which it was not detected. So I just started doing this work with the undergraduate. We just submitted this paper, but the main thing in this paper was just to track the outflow as a function of time. The outflow appears to be highly variable, which is weird. Because if you think of like a TDE where stuff falls in, you have high amounts of accretion, there's one ejection, and then as the overall accretion drops, you shouldn't see any outflow, right? However, that's not what is happening here. The outflow keeps coming on and off depending on what data you look at and when you looked at it. So the next big thing is obviously to do phase resolved X-ray spectra and try to see how this outflow changes over the phase of the QPO. And that's a bit more involved. And yeah, that's the next step for this one. So one of the main points I want you to take away from my talk is that maybe there are these recurring outflows present in all these systems. So I want to make a quick comment about the time lags. So this is, on the left side, I'm showing you a discrete cross-correlation function between 0.3 to 0.7 keV light curve and 0.3 to 1.3 keV light curve from Euroqb1, which again is shown here from Ricardo's paper using just the light curves. Basically, I'm cross-correlating and making it more quantitative. On the left side, you can see that it peaks first sorry, it peaks first in the hard. It peaks first in the hard, which means there's a negative lag. So the same trend is seen for all the 4 QP systems that are published. So this is the Euroqb1, where, so this is actually a typo. The hard comes first, then comes the soft. So Euroqb2, you see the same thing. The hard comes first. Forget this, hard comes first, then comes soft. Same thing with GSN, hard comes first, then comes soft. But here is the crazy source. It's the reverse. The soft comes first and then hard. You gotta switch it. But it's the reverse of what is seen in the 4 QP systems that are published. So I think any model that you want to propose should take care of these aspects. The ultrafast outflows that repeat, and then all types of lags, soft lagging hard, hard lagging soft. And then importantly, the observed range of quasi periods. So you got systems going from 2.4 hours all the way up to 20 days. And the most important thing is there's no correlation with the black hole mass. Right? If you have at least the M sigma black hole mass, there's no correlation. And then maybe I think Joaquin pointed this out. There is no fixed, there's no fixed temperature evolution, cool, warm, cool, that GSN 069 proposed. That may not be happening for all these systems. So something to keep that in mind. And most importantly, whatever model you have, you got to take into account the stochastic nature of these bursts, that the fact that they're not strictly periodic, that model has to explain that. So now I'm going to talk about the model. If I say something, don't start throwing your eggs and whatnot at me. I'm an observer, but I'll try to do justice to the other something. So the model that I'm going to talk about is a perturbing orbiter model, which induces the outflows. And the basic idea is as follows. You have this AGN with some sort of a low density medium around it, low density accretion disk. And there is an object that is embedded in an inclined orbit. So it's not coplanar, it's in an inclined orbit. Every time this object punches through, it pushes a lump of material towards the magnetic poles. And then that is when an outflow is launched. If you happen to be aligned with the polar region, then you see a blob coming in your direction. And this happens once every orbit. So that is what is going to be shown in this simulation. There on the top left side, I'm showing you the side view of the accretion disk. That's the object embedded in an elliptical orbit, not a circular orbit. That's why you see these funny patterns. And then here I'm showing you the bulk Lorentz factor. And this is the m dot out. This is m dot out plotted, top cone and then bottom cone. So basically the same thing. And this is m dot in onto the black hole. So accretion rate onto the black hole. So you see, if you happen to be aligned along this side, you see these blobs coming in your direction every time this thing goes and punches through the disk.
So I didn't understand, the object punches through, that pushes material that is funneled along magnetic field lines, feeding the black hole, and then that produces an outflow, which is what we see. That's a statement.
Yes. So the magnetic field is what is driving the outflow. It's not the radiation pressure. It's the magnetic field.
I guess that's what I don't get. If I have a disk, I punch through, then I expel gas, that would be channeled more easily along field lines.
Yep.
What I'm trying to understand is that you're saying what is perceived as an outflow is a material being funneled through those field lines, or as time goes by, that material will presumably end up being channeled towards the black hole, and then that may be emit an outflow. That's what I'm trying to understand. If the outflow is a direct result of the punching through, the material being following field lines locally, so to speak, where this happened, or the process could be that mass will end up being loaded into the black hole, which may end up emitting an outflow.
No, it's the former.
Okay.
If I understand your question correctly. There's no loading. Well, the loading comes in the next slide.
Okay.
Then, sorry, if it's the former, then you would see only sources that are perfectly safe on.
Yeah, so
Sorry.
so that's what I'm saying. The QP in this model, the only sources we can see are the ones very aligned with the poles.
Okay. So that.
Just like sort of like a GR. Yeah.
I mean,
not
you
exactly.
have a few sources, so that might be consistent, but
Yeah, I mean, the rates.
I mean,
are
it's a very
something-
specific thing to
Yeah.
observe sources just based on.
So that, I mean, that, you're asking a question about rates, right? That's what you're getting at.
And is this model capable of producing the right luminosity and energetics that you were saying in the?
Yep. It is.
But not for the QP sources, for the QP or the outflow sources.
Actually, yes, for the QP sources too. I'm gonna talk a little bit in the 2 slides I have. So here's the,
So, just because it's the other slide, so but they have like QPs have a presence which evolves like an altitude of 4, at least in GSM 69, which is not then a native. It's more like a finished disk, so this simulation wouldn't apply to at least a majority of the QPs with a soft X-ray quiescence.
so I would say majority of the QPs are actually very low heading to luminosity. Like
But-
ER QP1, ER QP2. The
Okay,
volumetric
wait.
luminosity is quite low if you
But-
take the M sigma mass.
Low luminosity wouldn't give you a soft X-ray spectrum by definition, it wouldn't be a finished disk. So if the low end iteration comes from the estimate of volumetric luminosity and the mass,
Yeah.
that's way more uncertain than the fact that we see soft X-rays.
Yeah, soft X is from a TDE. That's the second part of the like model that I'm gonna mention. So anyhow, let me just like go through and then we can discuss. So the idea is you have this black hole with an AF. And then there's an embedded object that is going around. It's been going around for tens of thousands of years, perhaps hundreds of thousands of
Oh,
years.
that's a
Pre-existing, yeah. So pre-existing memory. And then you have a TDE that comes in, and it just shines. And then it basically energizes the central black hole. And therefore, in that X-star modeling, it is giving you a new bright source that can illuminate the presence of these, the secondary object. So all it is doing,
Right,
the TDE is essentially providing material,
right.
energizing the central black hole.
So it's not that state of plunging to data that gives you
No,
right
no,
luminosity.
so soft X-rays that you see is from the TDE, the newly formed accretion disk. So the idea is, the supermassive black hole, AF, and then this going around. And you don't see this before the TDE happens because, well, this source is what, 10 to the 40 or something ridiculously low. So the outflows were launched even before the TDE happened.
Oh,
But you never see them
Okay,
because
okay.
we don't have like Athenas flying around,
Yeah.
So we have
No,
XML and
sorry,
Tensor.
yeah, sorry.
So
That's fine.
the TDE comes in and then makes a bright X-ray source. And then I'm happy to be looking around here, this bright X-ray source will shine and will make you see the thing. So the thing that is interesting to me at least is with this model, there's really only 2 parameters, main parameters. One is the eccentricity, because the eccentricity can explain the highly irregular nature of the burst. And the geometric orientation can explain the lags.
So I'm sorry, what is, so the TD disk is not affecting this corona? I mean,
Because the objects, if you take the M sigma masses, the embedded objects are much further out.
okay, for this source, but not for QP. I mean, for QPEs, the orbital periods are comparable to the tidal radius for a TD, right? So this is for the, for this other, for your new
So
source.
for these, at least the 2 ones that I talked about.
Okay, all right.
So here's the thing that I think Elisa asked about QPEs, how this model can explain QPEs. So the thing is, based on the simulations that they did, if the orbit is highly eccentric, the secondary can get really close to the ISCO of the black hole, and it can modulate both m dot in and m dot out. Right? If we can come really close to where the X-ray emission is coming from, you disturb that flow, you can trigger m dot in fluctuations. Right? So that's what is shown here.
But
Where you see this burst in the m dot in and also m dot out.
What do you call M dot in?
The
That's the
accretion rate on
accretion
the
rate
black
on the
hole.
black hole.
And-
But wouldn't that be smeared out by the, viscous time?
That's what I'm saying. It has to be highly eccentric. It has to be really close in. Viscous times are short.
But then what's the nature of the companion? If it's a star, it's already gone. No, I mean, it's well inside the tidal, right?
But what is the MRE? Is it
It's a black hole
IMPH,
then, yeah.
stellar mass black hole, star?
Yeah, I mean, that's actually, yeah, I've got some slides about that as well. So the other idea is if you have low eccentricity, then it's not able to modulate the accretion rate onto the black hole. And that's why, you don't see it in the continuum X-ray light curve, like in the source that I showed you. We don't see it in the continuum X-ray light curve. We only see it in the outflow band. Yeah, so anyhow, I can talk about things, but in the one source that I showed you, actually, this model, you can compare the strength of the outflow to the observations. In this model, the strength of the outflow is directly proportional to the size of this object. So if you compare with observations in this particular source that I showed you, it actually is an intermediate mass black hole. So these are some of the plots showing that. So this x-axis showing you the uncertainty on the primary black hole mass. The y-axis is showing you the influence radius of this perturber. And what this is saying is that in order to match the observations, this secondary has to be between those mass range. And then this particular source was also a TDE. Here are all the light curves convincing it's a TDE. But if it's a TDE, then we know that there is a rate for TDE, right? And if it's an intermediate mass black hole plus supermassive black hole, there's a gravitational wave in spiral time. So before they in spiral, we need to have at least one TDE to see it. So if you do that kind of argument, you'll see that for a perturber that is 10 to the 4 or more, the gravitational wave in spiral time is actually less than 10 to the 4. So you cannot even have one TDE under here. So in order to have at least one TDE, this has to be to the left. In which case you can constrain it better to be 100 to 10 to the 10,000.
So I just want to understand, so the constraint on the mass of the black hole is you need its interaction radius to be with the disk to be large enough, right? I mean, that's really where it's coming from, right? It needs
to. So the bigger the object, the more gas it can push.
Right. So you need its Bondi radius to be large enough, or whatever you want to call it.
Hill sphere, yes.
Hill sphere. So you can do that. You can do the same thing with a star, because these stars, these black holes that are orbiting through the disk at 0.1 c, to the Bondi radius for a 10 to the 3 black hole is basically the same as a solar radius.
If it has strong winds, right? That's what you're talking about. Strong winds. A star with just the geometric cross section of the star is comparable for a 10 to the 3 Bondi at 0.1 c. We could talk about. Yeah, so I have a plot for stars of different types as well.
Oh, okay.
We thought about that, so maybe.
Okay, I'm just wondering why you necessarily have.
Okay, so I've talked about all the awesome things the model can do, but I must talk about the caveats. So the biggest caveat is, one, we are assuming it's an ADAP, like a low density disk. So there is no back reaction from the disk onto the object. So the object is not, if it were a thin disk, the thing would just align with the plane within like 2,000 years. So if it's like a thin disk that is being hit by this object, it will grind down to the plane of the black hole within like 2,000 years. So it doesn't work. So the other thing is, these are mostly 2D simulations. The thing with 2D simulations for people who do this stuff is that there's the MRI, which is driving the accretion. This actually decays in the very innermost regions of the accretion flow. So it becomes after a couple of cycles. So like a few hundred days in the one case that we looked at. So we really need to do 3D simulations. And of course, we've explored a bunch of different structures of magnetic field and spins, and they seems to be working, but that needs to be thoroughly.
Can you say one more word about the magnetic field? So what would happen? So I understand the need for magnetic field for the disk to accrete to begin with, but forget about that for 1 second. What would be different in the model if the magnetic field were not there to channel the mass of the outflow? How would the results change?
I mean, if there's no magnetic field, this model wouldn't work.
Why?
What is pumping it out? In this model, the object is pushing, but what is going to make it launch at this fast speeds? Like
maybe I'm missing something. I thought, naively, if I have a slab of gas,
yeah,
and I push through,
yeah,
then for a given amount of energy that I'm getting as an input, what the geometry of magnetic field is gonna tell me is where that outflow is directed.
Correct. So are you talking about like more like Blandford?
No, actually that's the reason I don't want to get into anything complicated. My point is that in the absence of magnetic field, there will be still gas that is being producing an outflow.
From the disk, there's the persistent outflow. Yes, I have a plot about that as well. Persistent outflow without the perturber. Is that what you're talking about?
Now, I'm trying to understand, if I have a slab of gas,
Mhm.
and then I, give the object coming through, pushes, some fraction of that material.
Yeah.
That produces an outflow.
If
Without-
the escape velocity is, greater than it has to have enough velocity to escape the black hole's gravitational field.
And you're arguing that the magnetic field would alleviate that constraint?
In this case, yeah. So the magnetic field is helping it reach the escape speeds.
So do you want to finish off the slides?
I
and
know,
then come
that's
back?
nice. So anyhow, the role of TDs. So in this crazy Swift source, we had the same thing, no detection early on. Then there was this outburst that started doing the thing. Assess important light, TDE, this source, the outburst. Anyhow, the TDE role, I think, is basically pre-existing memory plus TDE could explain at least a fraction of these populations. So like I said, the idea is you have this object going around, but you don't see anything from it. You never actually detect anything. There's also launching outflows there, but you don't detect it because there's no ionizing continuum to show us that there is something there. When you have a TDE, you have a very strong ionizing continuum. And this object, when it punches out, the blob of gas is absorbing the X-rays, and then that's what you see. So I'll leave it there.
So you mentioned that it couldn't be a thin disk because it would grind down the inclination of the emery to after a few thousand years or something.
There's a plot depending on where it is.
But I mean, you're assuming there that obviously the supermassive black hole has some spin presumably, and you're saying the inclination of the emery's orbit. But if the TDEs are coming in with different, inclinations, couldn't the outflow be aligned with the angular momentum of the accretion disk of the TDE rather than the black hole spin? I mean, are there some simulations to suggest that?
So you're talking about TDEs in general. So you're asking if the.
So in general, you're going to have TD stars coming in from all different directions and getting disrupted. And so they'll form transient, accretion disks with, angular momentum in different directions. And so you're concerned about the kind of emery being equatorialized. If the different, TDEs have different directions, why would it be a worry about they'd have different equators?
Good point. If that disk is kind of misaligned, you're saying that.
Certainly maybe it could get equatorialized, but there's no reason to assume initially that the TDE accretion disks would be, equatorial with respect to the black hole spin.
Yeah, I mean, it's more pro for this model, so, yeah.
I also had a question. So, I mean, you're saying it's not, and there's not going to be a thin disk present, but then, and then you also mentioned in the talk, you might have the superposition of different bodies in the X-ray spectrum. So how sure are you that these outflows aren't just due to uncertainties in how we're modeling the X-ray emission from these disks?
So the sources I showed, I've already taken care of that. I've tried it with different continuum models. So maybe step back a little bit. So end of the day, any signal anyone has ever detected is only as strong, as robust as their continuum model, right? So in this case, we've assumed a bunch of continuum models. In the main source that I talked about, we assumed a thermal model. We assumed two thermal disks. We've assumed a thermal plus power law. We assumed, freeing NH of the hose. So we've considered different things. In all those cases, we also assumed that there is a warm absorber much further out that can contribute and similar signal. So in all these cases, we still see the outflow signature with the same parameters, more or less, within the 90% uncertainty in all these models, all the continuum models. So we tried different continuum models, it's still there.
So there has been, I should know this. So there has been like a proper model selection done for each of these models, and you even say like some of the slim disk models from like Radar.
I'm not very slim disk model. The slim disk model, all it does is adds a little fatness to the hardness of the X-rays, right?
Yeah, but then if you combine it with like a warm absorber, you might get some waves.
So you want to add a warm absorber, slim disk, and one more thermal black body.
But yeah, I mean.
Yes, you can add whatever
main
like,
point is
things
that,
and make it work. And at the end of the day, you have to ask, does it make statistical sense to like make your model super duper complicated? We have a prior from all the TDEs that they're all thermal spectra. So why would
they're
you
not like 14 and IS2 like in the Cara paper that she fits.
No,
in.
it's wrong. We just wrote a paper saying that it's a pileup effect. What she was feeding in the high energy band is just a pileup.
Okay, I'm not aware of that.
Yep. So that's the paper that we write. That there's no need for two disk black bodies in particular. It's just a pileup that they were feeding.
Yeah, that's only because.
Oh, okay, I was just gonna ask, I have a question and then a comment. So my question is whether you see any evidence for velocity evolution of these features before it goes away. Because my comment is that generically, if you punch a star through a thin disk, it will create a cloud of debris. And if the star is moving at Keplerian, that cloud of debris will have an energy which is comparable to the binding energy of the material. And so you will actually cover up that cloud of debris will actually go will both surround the source of hard X-rays that are coming from the collision itself, as well as some of it will go in front of the black hole. So I think, even a scenario where the disk is thin, we should have predicted this, that you could see absorption features from that. So that was my comment. But my question is, in this scenario, if it's actually coming from absorption of the cloud itself that was ejected from the disk, like a good supernova, you would see the outer layers, the fast expanding layers produce the absorption first, and then as the emitting surface is moving into lower velocity layers, you should see that absorption feature move to lower energies, less Doppler boosted. So that's why I'm asking the question: is it whether you see any evidence that maybe there's velocity evolution in these features, a slowing down?
So within the error bars, I would say, I'll show you the plot. You can decide later. It's in a different presentation. I'll show you the plot.
Okay. The answer is no, or not within there.
At least nothing like super obvious that I could tell, like, oh.
So it just looks like a constant speed. Okay. But
I'll show you the plot so you
Okay.
can decide for yourself.
So anyway, that's fine.
That's two questions.
I'm not sure I understand why the object punching through the disk while you are assuming the emission to come from the fact that you have a TDE at the same time. Like I didn't understand, but
Okay. So what I'm saying is, before the TDE happens, like if you go here, maybe it's a better way of showing you. So can you see here?
Yeah.
So that the top panel is a long time ago, before the TDE happened, right? So you have a very low luminosity system because we don't even detect them in X-rays with like XMM or EVO zeta, nothing, no detection. So they were treating it less than 10 to the minus 5 Eddington. So ADAF is justified. So you have a supermassive black hole, the mass you get from optical, if you believe that. But you gotta start somewhere. So that's your black hole mass. So if based on that black hole mass, it's an ADAF. You have this object that is going around, it's doing its thing, punching through, but you're not going to see anything because, well, there's no radiation illuminating this blob. Right? Something has to be absorbed for us to see it, right? But the TDE simply like makes it bright.
Yeah.
And then, yeah, it's shining. And then if you don't have this perturber, you just see the continuum. You just see a black body or whatever. But because of this object doing its thing, periodic, and then because it's eccentric orbit, the time it hits the disk is also very irregular, in fact.
Yeah, last question, Brennan.
Very, very simple, but what's the size scale again on these? I know it depends on the system, but approximately.
So for this, that
For the orbit of the perturber.
So one of the ones I talked about, the 20 QC one, there the period is 8.5 days. The black hole mass is 10 to the 7.5. So this object is at twiddle 90 RG or 100 RG.
Is it a short question?
Oh, just a quick question. When you said, because the perturber is eccentric, it makes these things irregular. I mean, we know like geodesics occur and things. Certainly the period is you know, the radial azimuthal and polar periods are, you know, more complicated for Kerr geodesics than some nice closed Keplerian thing, but it's not really irregular exactly. I mean, that would be really a smoking gun that you've got a perturber if you could actually match up these things with collisions. I mean, I guess it's, in principle, you've got the period of these things is short enough and the duration, as we heard this morning, is long enough. You'd have more than enough data to do, in theory, to do that. In practice, you probably don't yet.
Yeah, that's what I think Ricardo is doing. It's very important, right?
That'd be great to see.
No. Yeah, shall we thank TJ once more?